By the end of this video, you'll understand how scientists can predict the pressure inside a balloon, the air in your car tires, or even the atmosphere on another planet, using just one equation. And what exactly PV equals nRT means, how to use it, and when it doesn't quite work as well as we'd like. Before we dive into the math, let's start simple. We all know since third grade that a gas is a state of matter where particles are spread far apart, moving at high speeds, and with no fixed shape or volume. Unlike solids, which have tightly packed particles, or liquids, which have particles that are close but can flow, gases are like a crowd of hyperactive kids running around a giant playground. Gases can expand to fill any container, and their particles are in constant, chaotic motion. The ideal gas law works on an imaginary kind of gas, the ideal gas. Here are the assumptions we make. The particles themselves have negligible volume compared to the container. There are no attractive or repulsive forces between particles. Collisions between particles and with the container walls are perfectly elastic, no energy is lost. The particles are in constant, random motion. Of course, no real gas behaves perfectly like this, but many come close, especially at low pressure and high temperature. Now, the star of the show, PV equals nRT. Here's what each letter means. P pressure, measured in Pascal or atmospheres. V volume, in liters or cubic meters. And number of moles of gas are the universal gas constant, which is 8.314 joules per mole Kelvin, or 0.0821 liter atmospheres per mole Kelvin. T temperature, measured in Kelvin. Remember, no negative temperatures here. This equation tells us that if we know 3 of these variables, we can calculate the 4th. Let's try it. We have 2 moles of gas at 300 Kelvin in a 5-liter container. What's the pressure? PV equals nRT. P times 5 equals 2 times 0.0821 times 300. P times 5 equals 49.26. P equals 9.85 atm. So, the pressure inside the container would be about 9.85 atmospheres, nearly 10 times the air pressure at sea level. This isn't just textbook stuff. The ideal gas law shows up everywhere. Meteorologists use it to predict how weather balloons expand as they rise into the thinner atmosphere. Scuba divers rely on it to know how much breathing gas is in their tanks. Drivers notice that tire pressure changes with the seasons. Colder temperatures mean lower pressure. Warmer temperatures mean higher pressure. Even bakers use it, though they might not realize the bubbles of carbon dioxide in bread dough expand when heated, making the bread rise. So, does PV equals nRT always work? Not exactly. At very high pressures, gas particles are forced close together, and their own volume becomes significant. At very low temperatures, particles move slowly, and attractive forces between them become important. In these cases, real gases deviate from ideal behavior, and we need more complex models like the van der Waals equation. The ideal gas law is a beautifully simple equation that connects pressure, volume, temperature, and the amount of gas. It works surprisingly well in many situations and helps scientists and engineers understand everything from deep-sea diving to outer space exploration. Remember, PV equals nRT. Small equation, huge impact. Thanks for watching, and keep asking questions, because science is all about curiosity.